These notes are on multiplying and dividing complex numbers. So we're going to start by looking at how we multiply complex numbers, and this is going to feel very familiar because you can use any of the methods you use when you multiply binomials. So that could be FOIL, it could be the distributive property, or it could be the box method, which is my personal favorite. So if I'm using the box here with this first example, the idea is I can set up 1 minus 3i times 2 plus 5i, and then just multiply in to each box. So I get 2, negative 6i, 5i, and I get negative 15i squared here. So we can, I times I is I squared. Now we're going to pay special attention here because we have to remember that I squared is negative 1. So this is the same thing as negative 15 times negative 1. And that's going to become positive 15, right? So then when I go to combine my like terms, I'm going to have 2 plus 15 to combine, and then I'm also going to have the negative 6i plus 5i. And that's going to become 17 minus 1i, or I'm just going to write I. And that would be my final answer there, the 17 minus I. So when you multiply two complex numbers, you get another complex number. So here's a you-try problem for you guys. It's 1 plus 5i times negative 3 minus I. So do your best on this, and then you can continue with the next part of the video. So I'm going to introduce a new vocabulary word to you guys, which is something called the complex conjugate. And the complex conjugate of a number a plus bi is a minus bi. Okay, so we kind of have these pairs of binomial complex numbers where one is the plus and one is the minus. And the complex conjugate is important when we're dividing complex numbers, because something interesting happens when you multiply a complex number by its conjugate. And we're just going to multiply it out now so you can see the relationship. So I'm going to multiply using the box and put a plus bi, a minus bi. So I get a squared abi, negative abi, and negative b squared I squared. Now for that b squared I squared, remember I squared is negative 1, so this is negative b squared times a negative 1. So that's really going to become a positive b squared. Okay, another thing to notice here is that I have plus and minus of that same middle term, the a plus bi and minus a plus bi. So those are actually just going to cancel out, because if we actually add everything up, I get a squared plus a plus bi plus a times a plus abi minus abi plus b squared. So from there, the middle two terms cancel, and I'm left with a squared plus b squared. So it's really nice that when you multiply a number by its conjugate, this is actually, there's no I in this number. This is a real number. So that's useful to us when we're dividing, because it helps us get rid of a complex number in the denominator of a fraction. So now let's take a look at the division problem. At a division problem, and you can see what I mean by how useful the complex conjugate is going to become. Okay, so in this problem I have 6 plus 3i, and I'm just going to rewrite it as a fraction, divided by 7 minus 5i. okay? And what we're going to do here is we're going to multiply the top and bottom of the fraction by the complex conjugate of the denominator. So let me write that down for you. So multiply, that's really messy. Let me try again. Multiply the fraction by complex conjugate of the denominator. And I forgot to say, multiply the fraction. We want to do top and bottom. We'll talk about why in a minute. So what that looks like here is to multiply top and bottom by the conjugate of 7 minus 5i, which is 7 plus 5i. And since I'm really just multiplying by 7 plus 5i divided by 7 plus 5i is just 1. That's the same thing over itself. So that's not changing my expression at all. It's keeping it equivalent. So when I think about this multiplication, in the denominator, if you remember from the previous slide, when you multiply a number by its conjugate, you're going to get a squared plus b squared. So in our case, our a squared is 7 squared, and our b squared is 5. So we do a squared plus 5 squared. 7 squared plus 5 squared. And in my numerator, I'm going to have these two binomials, 6 plus 3i and 7 plus 5i. Okay, so I actually need to do that multiplication out. I'm going to kind of go over to the side to do a little box. And setting up 6 plus 3i, 7 plus 5i, get 42, 21i, 30i, and 15i squared. That means really that's 15 times a negative 1. So that's going to become a negative 15. So coming back over to my division problem, I now know this is going to be equal to 42 minus 15 plus 3i plus 5i. No, sorry, not 3i and 5i. Plus, I was looking on the outside instead of the inside. Plus 21i plus 5i. Oh. 30i. Okay. All over 49 plus 25. Because that's 7 squared and 5 squared. Continuing to simplify, I get 42 minus 15 is 27. And then if I add 21 plus 30, I get 51i. Divided by 49 plus 25 is 74. Okay, so the last thing I'm going to do is I'm going to split the 74 because the idea here is that I want to express my final answer in the form a plus bi, but right now I have like a plus bi divided by a number. So to get it in that standard form of a complex number, I can write it as 27 over 74 plus 51 over 74 times I. And now I have my solution to the division problem in standard form, and it was all because I was able to multiply by the conjugate.